Today we're going to look at more trigonometric substitution. I really like trigonometric substitution because it represents this, it's a good example of this idea of transformation. We trade our x integral for a theta integral, and we integrate that one. Then when we have our theta antiderivative, we undo the trigonometric substitution to get back to our x antiderivative, which is the one that we want. Yesterday, we broke it down into three cases. The tangent case, a squared plus x squared. I put them in a different order today, so it's super inconsistent. So we've got the tangent case, a squared plus x squared. We got the sine case, a squared minus x squared. And we've got the secant case, x squared minus a squared. So what we want to notice is that more than just the two terms becoming one term, which is the big operation in trigonometric substitution, what we're looking for is some kind of quadratic. And here we've got all of our quadratics covered. We've got the secant case with x squared minus a squared, where we have quadratics with real coefficients, with real zeros. Our sine case, also quadratic with real zeros, and our tangent case, which is quadratic with complex zeros. These are all two-term quadratics, but we're only completing the square away from a two-term quadratic when we have three-term quadratics. So if we have x squared plus 4x plus 13, we want to start recognizing that as the tangent case, because x squared plus 4x plus 13 is just x plus 2 squared plus 9. So it's a tangent case with a substitution. But we're getting ahead of ourselves at that point. The big idea is we trade our x integral for a theta integral, which is usually products of powers of trig functions. And the products of powers of trig functions that show up in your theta integral are definitely not going to be substitution integrals. Because if there's a substitution in your theta integral, there was a substitution in your x integral. Abandon trig substitution, go back and do the substitution up there. Moreover, the theta substitution will tell you what the substitution should have been in the beginning. We'll see an example of that soon. All right. I think I've got my examples loaded for today. It's funny because I talk so freaking much. I do like 2 examples a day, mostly because I won't shut up. So there's that. All right. So let's do an example that does not do what happened yesterday. Yesterday, we had the easiest examples. We did our trigonometric substitution, and we essentially everything canceled out, and we just had to integrate 1 dx. And so when we undid the trig substitution, it was very simple. We just had to solve x equals 5 tangent theta for theta. So theta was tangent inverse of x over 5. We're going to have a little bit more to do with here. So we're going to go into the details of undoing the trigonometric substitution today. We're going to expand on this part right here, undoing the trigonometric substitution. So let's take a look at this example. We've got the square root of 25 minus x squared. The thing that stands out from this example is the 25 minus x squared. It's in this messy square root. That messes everything up. I can't just distribute the exponent over the terms, because that's not how numbers work. We identify this as a sine case with a equals 5. So 25 minus x squared, not the square root part, just the 25 minus x squared part says this is a sine case with a equal 5. So that makes our substitution x equals 5 sine theta. That's going to replace the x in 25 minus x squared. Looking ahead, this is going to become 25 cosine squared theta. That's the whole point of doing this. We need to know that, start recognizing that before we even begin writing stuff down. We need to see this 25 minus x squared, recognize this is sine case, and know that this is going to become 25 cosine squared theta. Dx is going to be 5 cosine theta to theta. Now we're ready to make our substitution. The important thing to note is that we know what's going to happen here, because it's always the same thing what happens when we do this. So let's do our substitution. Dollar says I did not make this long enough, because I never make the radical long enough. X has become 5 sine theta. Told you. I don't know why. Once we decide on our x and we calculate our dx, we put those things into our integral. This is one of the integrals that when we become good at trig sub, we're not going to write, because we know what's going to happen. But right now we're new, so we write stuff down. When you first learn algebra, when you write 5x minus 4x, you should write 1x because you're new. The 1 is understood when we just write x. But when you're new, you don't understand things, so you just write 1x to emphasize what's going on. Now we're going to work just on this square root part. 25 minus 5 sine theta. If I multiply this out, this is all going to be a square root of 25 minus 25 sine squared theta. So that's going to be 25 times 1 minus sine squared theta. And so that's going to be the square root of 25 cosine squared theta. The square root of 25 cosine squared theta is going to become 5 cosine theta. So our integral, show one more deconstructed. The square root of 25 minus x squared has all been replaced with 5 cosine theta. And I still have from my dx 5 cosine theta d theta. And so now we can simplify and we'll be at our theta integral, which is going to be 25 cosine squared theta. So we have just done that first step. We have done the trigonometric substitution. We are at the theta integral. Any questions on this first step? Once you've done 1,000 problems, you'll know what's going to happen just by looking at the integral. Now that we're at the theta integral, we need to remember the integral of cosine squared. The integral of cosine squared, theta, is going to be theta over 2 plus 1/2 Let's see, how should we write it? I guess sine of 2 theta is the way we normally wrote it. What we're doing is we're integrating the products of powers of trig functions. I'm actually going to write it down. So our strategy for integrating products of powers of trig functions, when we have even powers of cosine, is to replace cosine with the double angle identity. So right now we're in the process of, we're going to do this process integrate. We're going across to find the antiderivative in theta. Cosine squared theta with a double angle identity is going to be theta over, well, it's going to be 1/2 plus 1/2 cosine of 2 theta. Once we're doing trigonometric substitution, we know we also have to get ready running in the background, integrating products of powers of trig functions that are not substitutions. That's extraordinarily specific, but there it is. So we use the double angle identity. Cosine squared is 1/2 plus 1/2 cosine of 2 theta. Now we can actually do the integration part. The integral of 1/2 d theta is a 1/2 theta. The integral of cosine of 2 theta is 1/2 sine of 2 theta. I'm going to put plus c to indicate that we have done our integration. We are now at the theta integral. How's everybody okay? Rad. And now we've got the new thing for the day. That theta is going to be easy to replace. Notice that we started off this whole process by saying x is equal to 5 sine of theta. So theta is sine inverse of x over 5. That's no problem. That'll be easy to replace. The other problem that we have, though, is that sine of 2 theta. I can't just put sine of 2 times sine inverse of x over 5. In this class, with other teachers, they might allow it, but you are not allowed to write cosine of sine inverse, or sine of sine inverse, or tangent of secant inverse. That is unacceptable notation. That's like saying, how much do you have in your pocket? 10 plus 5. You don't give your reader a problem to do unless you're the teacher. So you can't tell your reader the answer is the sine of cosine inverse, or in this case, the sine of 2 sine inverse. Unprofessional. Don't answer questions with questions. Unless you're a teacher, because we do that shit all the time. So here's what we have to do. First of all, I've got to get rid of the 2 theta and write things in terms of theta, because that is how things are related. So what we're going to do, first of all, I'm going to distribute the 25. So 25 over 2 times theta plus 25 over 4. And I'm going to replace sine of 2 theta with 2 sine theta cosine theta. We double angled our way into this. We got to double angle our way out of it. So I did 2 things on that step, so nothing up my sleeves. distribute the 25, and the double angle identity on sine of 2 theta. The 2 and the 4 are going to cancel each other, are going to cancel. The 2 from the 2 cosine theta sine theta is going to cancel out one of the 2's in the 4. Theta, I know I can replace with sine inverse of x over 5. And I also know that sine theta is equal to x over 5. So theta is going to be sine inverse of x over 5. But this sine theta right here, that I can replace with just x over 5. That's just the middle step between x equals 5 sine theta. Solve that for sine of theta. Sine of theta is x over 5. The problematic one is this cosine theta. I need to write cosine theta in terms of x. And for that, we need to do the triangle thing. So we got to do some trigonometry. So this is what I call the triangle thing. Notice that sine of theta is x over 5. And in a right triangle, that means x is the opposite and 5 is the hypotenuse. For cosine of theta, we need to know the adjacent. So what we're going to do is imagine a triangle. Since sine of theta is x over 5, x is opposite and 5 is hypotenuse. We can use that to calculate the adjacent. So the adjacent side is the square root of 25 minus x squared. And gosh, that sounds familiar looking at what we started with. So now we can write cosine of theta is square root of 25 minus x squared over 5. So theta gets replaced with sine inverse of x over 5. Sine of theta gets replaced with x over 5. Cosine of theta gets replaced with square root of 25 minus x squared over 5. That's adjacent over hypotenuse. Because we do the right triangle thing. Now all we have to do is clean up those 5s, and we have a nice answer. How's everybody okay? Incorrect. You are not okay. Don't just say yes because that's what you're supposed to say. You can be honest. You can be like, oh, this is weird. Because it is a little bit weird. I don't know. Maybe this is okay. Maybe you're all cool with this. Look at the huge amount of things that we had to remember for this. We had to remember how substitution works at its core. All the x's have to be replaced with thetas. That includes the dx. And we're doing things a little bit differently. We're just replacing the x, and then we're going to replace the dx with all these expressions in theta. Then we had to remember our trigonometry. All we needed really was a Pythagorean theorem or a Pythagorean identity. Then we had to remember how to integrate products of powers of trig functions, specifically even powers of cosines, which are not substitution problems. So we had to remember our double angle identities. Then at least we had an easy time integrating. But then we had to remember another double angle identity. And then we had to do some more trigonometry to get ourselves back to our answer in x. And it seems like a lot of work to do on a problem that after Calc 2, you're never going to have to do again. But coming up with the answer is not the point. And in a math class, it's almost never the point coming up with the answer. Questions? So the two examples yesterday were just to get the basic flow of things. Here's where we had the first challenge in the integration step, where we come up with products of powers of trig functions that aren't substitution problems. But then we also had to do the triangle thing to undo the trigonometric substitution. How's everybody okay? Yes. Yes. So the triangle thing was based on, we have x equals 5, can't see that part. X equals 5 sine of theta. So if we turn that around, we can see that sine of theta is x over 5. And if sine of theta is x over 5, that means we can write x as the opposite and 5 as a hypotenuse. The sine is opposite over hypotenuse. So I draw a triangle where x is opposite theta, a right triangle, where x is opposite theta and 5 is the hypotenuse. Then I use the Pythagorean theorem to get the adjacent side. So I solved for the adjacent side. So that's how the triangle thing works. So we're pulling a lot of information about that from our initial substitution. X equals 5 sine theta. That decision tells us what dx needs to be. That's normal for a substitution. We look at what x is, we look at what dx is. But we also can figure out what the sine of theta is equal to. We can figure out what theta is equal to. And we can figure out what cosine of theta is equal to, all in terms of x. How's everybody okay? Let's take a look at the detail. Let's zoom in on the triangle thing for a minute. So in addition, let's talk about what we get when we make our initial substitution. Let's see all the things that we get out of this. So the x equals 5 sine theta, that's our initial decision, or that's our initial substitution. That's where this is all starting. From there, we have to get the dx, and these are the pieces that we need to do the trigonometric substitution. This is what takes us from the x integral to the theta integral. The other piece of information that we're going to need here is that 1 minus sine squared is cosine squared theta. These are the pieces that we need to do the trig sub, to get to our theta integral. Then we have to use our awesome integration skill, integrate the products of powers of trig functions. That's going to require some cleverness on our part because we have to know integrals of even powers of cosine. And then the other one that you're working on, secants and tangents. What secants and tangents do not require a trigonometric substitution? But we get other things from this. If we just start turning this equation around, we can see that sine of theta is equal to x over 5. And so theta is sine inverse of x over 5. In a sine of theta, if sine of theta is our substitution, that means cosine of theta could make an appearance in our theta antiderivative. So that means we have to go a little bit further and draw our triangle. You don't literally have to draw the triangle, but you have to think it. And so this gives us cosine of theta as square root of 25 minus x squared over 5. Six things, including our initial substitution. We decided on the x because of the case. Calculate the dx. We know we're going to need a Pythagorean identity. We're going to have to undo our trig substitution by solving for sine of theta and solving for theta possibly. And then we're going to have to do the triangle thing because cosine of theta might make an appearance. In the tangent case, it'll look a little bit different. In the tangent case, let's suppose that we set up to make the substitution x equals 5 tangent theta. If x is 5 tangent theta, then dx is 5 secant squared theta, d theta. We're going to need a Pythagorean identity, which is going to say secant squared plus 1 Oh, no, we're going to need the other one. Our 1 minus sine squared becomes cosine squared. And so our 1 plus tangent squared becomes secant squared. These are the three pieces that we'll need to get to our theta integral. Once we do the theta integral, we might need to know what tangent of theta is, because that could show up in our theta integral. So to undo the trigonometric substitution, the tangent of theta will be x over 5. If we need theta, then we'll just do tangent inverse of x over 5. And then on top of this, we might need to know secant theta. So we're going to do a triangle. But in this case, we know that tangent of theta is x over 5. So opposite is x and adjacent is 5, because tangent is opposite over adjacent. Sine is opposite over hypotenuse. Tangent is opposite over adjacent. And so what we have to do is solve for the hypotenuse. Once we have the three sides of the right triangle, we can write any trig function that we want. Sine of theta will be x over the square root of 25 plus x squared. Cosine of theta will be 5 over the square root of 25 plus x squared. In the context that we're working, we're going to be looking at combinations of secants and tangents, which means we're going to want the secant of theta, which is hypotenuse over adjacent. If, for example, we're in the secant case, because we're looking at x squared minus a squared. In this case, it would be x squared minus 25. That would tell us our substitution should be 5 secant theta. That tells us our dx should be 5 secant tangent d theta. We're going to need the identity secant squared minus 1 is equal to tangent squared. These are the three pieces that we'll need to go from our x integral to our theta integral. Then we're going to have to use our integrating products of powers and trig function wizardry to integrate the theta integral into the theta antiderivative. Then we're going to need to undo the trigonometric substitution. The pieces that we'll need: secant theta is going to be x over 5. If we need theta, that's going to be secant inverse of x over 5. We're going to have to do the triangle thing because there might be some tangents running around. When we integrate secants, we might end up with some tangents that we have to turn into tangents of theta that need to turn into x's. So secant is hypotenuse over adjacent. So our triangle our hypotenuse is x and the adjacent side is 5. So the opposite will be the square root of x squared minus 25. Because we've just integrated a bunch of secants and tangents, most likely the piece that we'll need is tangent of theta at this point. And so tangent of theta is opposite over adjacent. Questions? Don't think of it as backwards. It is a little bit, it's different. Because think about the structure. So this seems like a lot to remember, but that's only because it's a lot to remember. And you have to remember all of it all the time in perfect detail. But there's a lot of supporting structure that's going on here. Remember, all this is stuff that we have to remember while doing trigonometric substitution. And the first step in trigonometric substitution is deciding on the case. That structure in the case is going to help you remember how things are going to look. What made us decide the sine case is we saw a 25 minus x squared. And look at what showed up at the end, the 25 minus x squared. That's what made us think of the sine case in the first place. The trig identity that we have to remember is 1 minus sine squared is cosine squared, because 25 minus 25 sine squared became 5 cosine squared. So the structure where you decided the case is going to tell you what this blue identity should be. So don't worry about thinking about it as backwards. Don't worry about remembering 1 plus tangent and secant squared minus 1 separately. Use the case to help you remember these. Because this is the case information right here. The sine case is from a squared minus x squared. The tangent case is for a squared plus x squared. The secant case is for x squared minus a squared. Remember, if you remember that is the point of the trig sub, for this x squared minus a squared to become a tangent theta, or a squared tangent theta. Then you don't have to remember these separately. That make sense? It also helps you because the things that made you decide on these cases show up when you do the triangle thing. So there's a lot of supporting structure to help you remember everything. And that's a better way to think of it, as this one is backwards. Because when we say things like this one is backwards, it helps us right now in the moment for this one little thing. But that's way too specific. We're trying to become mathematicians. We need to understand all of it. This is one of the difficult things about trigonometry as well. One of the reasons that trigonometry is kind of difficult is that we normally like to learn things in a progression, but trigonometry kind of happens all at once, right at the beginning. As soon as we define our sine theta and our cosine theta and our tangent theta, and as soon as we put acute angles all the way around from 0 to 360, or from 0 to 2 pi, all of trig has happened. And we have to go into all these details. We have to pick what happens next. Make sense? Algebra is much more structured. Arithmetic is much more structured. The first thing you learn is addition. Unfortunately for our heroes, we don't really learn addition properly. We just learned a bunch of tips and tricks. We learned to add base 10. This is because our education system was not set up to educate people, or not set up to create educated people that understand things. It was more designed to create good factory workers who could stand on a line for 10 hours a day and do the same thing over and over again. Now, we want to achieve something different. We want to achieve people that are, we want to make people that are educated. There's a lot of friction because that's going to be incompatible with standing on a line and doing the same thing over and over again for 10 hours a day, 8 hours a day. There have been some progress made in the labor movement. Then, of course, machines have kind of taken over those standing on the line for 10 hours a day. So what used to take 100 workers now probably takes like 3 or 4, because they just have to watch over the robots, keep the robots in check. Any questions? Yeah, and it's pretty much always going to want the same thing. The sine case is always going to give you the, once you see the sine of theta is x over 5, you know what the cosine of theta is going to look like, because that's the one that you're going to do. We can figure out what tangent of theta is based on this, but we don't need that. We're integrating products, powers, trig functions. We're going to need sines and cosines. We're going to need tangents and secants. We're going to need tangents and secants, because those are the ones that go together. And we're reminded of what's going to go together by the relationship between x and dx. Derivative of sine is cosine. Derivative of tangent is secant squared. The derivative of secant is secant tangent. So they all kind of, they go together in those pairs. This is why, even though we had more trig functions, we don't bother with a cosine case or a cotangent case or a cosecant case. We just need to know how. Any questions? At this point, we probably know 6 trig functions. Is that correct? Sine, cosine, tangent, cotangent, secant, and cosecant. The problem is we don't want to say the 6 trig functions, because there are more than 6 trig functions. I'm not even talking about inverses. There's other ones. We don't really need the other ones anymore, mainly because we have machines. We have calculators that can calculate sines, cosines, and tangents to a great deal of precision instantly. We needed other trig functions. Like I'm that old. We needed other trig functions to deal with angles that are close to 0 and close to 90, things that are close to the quadrants. Because back in the day, if you wanted to know the sine of 37.5 degrees, you looked it up in a book. I shit you not, you looked it up in a book. You would be carrying a book around and you would turn to 37, then you'd go down to 37, and then find the 0.5, and then it'll list the sine of the angle. Maybe to 4 decimal places. I don't know if they ever made a book with 5 decimal places. That's kind of a ridiculous degree of precision. But then computers came along. Actually, in between, we had a slide rule. And then calculators came along. And then scientific calculators came along. And we don't need the books anymore. If you find an old trig book, you find an old trigonometry book, at some point in that book, they will list tables of values for trig functions. Now you've got to go way back, like way back, to find a trig book for high school students that had one of these tables in it. I'm talking about 1987. So I guess that wasn't too long ago, was it? Because I had one in my trigonometry book. Now I know that you all recognize that I am old and decrepit and very, very ancient. But people are alive today that did not have access to frigging scientific calculators. And we're looking that shit up in books. You know what I mean? Anyway, now I'm teaching a class, you only have to be in the room. One generation. It's amazing what comes and goes in one generation. Anybody remember CDs? CDs did not exist when I started listening to music. CDs came and went in my lifetime. I know you might still make mixtapes. We call them mixtapes because cassettes came along. And cassettes came and went in my lifetime. Anybody know what a floppy disk is? Floppy disks came and went while I was alive. At least 3.5 ones. Because the first floppy disks I had were the 5.5-inch ones. And they were actually floppy. Then we put a hard plastic case around them, but the inside part was still floppy. Everybody know what I'm talking about? Like 1 or 2 people are like, oh yes, I am interested in computers, the history of computers and computers. As far as I know, my Atari 2600 still works. For those of you who know what an Atari 2600. I need to repair the joysticks, but I can probably make the repairs with the soldering iron, so How complicated could it be? You know what I'm talking about? Does anybody even know what an hard 2600 is? I should bring it in. We could have a combat tournament. Combat the game. Came on a little cartridge. I would dominate you all. You would be all doomed in combat. It's not like actual combat, like actual physical combat in the real world. I'm completely incompetent at, as far as I know. I don't get into fights anymore. All right, that's going to do it for today. Tomorrow we'll look at more complications with trigonometric substitution because it's fun. Fun, goddammit. That's it for today. I'll see you all on tomorrow. Everybody have a good day. And thanks for playing.